Okay, so obviously I have fallen in the hard times here, and my digital visualizer is not working, so I'm literally just using my iPhone and taping this. Okay, so I want to start this video talking about dihybrid crosses. So due to independent assortment, which occurs during meiosis 1 and also meiosis 2. It happens during metaphase of meiosis 1 and 2, or metaphase 1 and 2, that the tetrads in metaphase 1 can line up on the metaphase plate in any orientation, and then also during meiosis 2, this chromosomes and their corresponding sister chromatids can point to either pole. So anyway, we looked at monohybrid crosses, and mono meaning one. Now this is addressing dihybrid crosses. So with dihybrid crosses, you're looking at two characters. Now, in order for you to do a dihybrid cross, there are a couple criteria. One is that they cannot be linked genes. And hopefully you watched the other videos where I had talked about what linked genes mean. So they cannot be on the same chromosome. And therefore, if they're not on the same chromosome, they're going to independently assort from each other. Now, with a monohybrid cross, you're looking at one particular character. With a dihybrid cross, you're using two different characters. Now, what the dihybrid cross did for Mendel was, after looking at his ratio of the phenotypes of his offspring, he had realized that these genes, they actually assort from each other independently. You guys be quiet, I'm taping. Okay, so couple rules about dihybrid crosses. The first dihybrid cross is you need to, make sure, I have kids watching me now, okay. So with dihybrid crosses, rule number one is that you have to simulate meiosis, okay. And that is basically independently assorting your alleles. Okay. The next thing you do is you set up the cross. And then the third is that you complete your cross. And then finally, what you're going to do is you're going to analyze your cross. Okay. Now, we'll go over each step in a lot of detail. So with step one, I am going to just have some, just do your traditional, can you guys get out of here? You guys, I'm filming for my work, okay? If you get out of here, I love you.
How much do we have?
Just whatever. Okay, so big A will be, let's see, yellow seed, and then big B will be round seed, and then little a is going to be recessive, and this is green seed, and then little b, which is going to be wrinkled seeds. Okay. So these are the genotypes. So let's put a little separation thing here. So here is the color of the seed, and this is like either it's wrinkled or round. Okay. So let's say we have two parents, and they're both what they call dihybrids, meaning that they both have one of each allele. Okay. Okay. So they both have one of each allele, so they will have the dominant phenotype. So hopefully at this point, you can discern from this genotype that the phenotype is going to be yellow and round. Okay? So the next thing you're going to do is you're going to simulate meiosis. So let's just look at this parent here. So we have the genes that code for yellow, or for color. And then we also have the genes that code for the, whether it's round or wrinkled. Okay. Now what happens during meiosis is these are going to split. So we have big A and little a here, and these are also going to split. So we have big B and little b here. Okay. So with this particular cross, because they're dihybrids, they can actually produce a lot of different combinations. So this allele, because of independent assortment, this allele can pair with this one. This allele can pair with this one, okay? Because remember, these are different genes. This can pair with this one, and this can pair with this one, okay? And so essentially, with this particular parent, the following genotypes that you can result from the gametes, okay, is that, okay, so, all right, so what results from here is that there can be different gametes that result from here. So this A can base pair with this B, and this one can pair with that one. So the different gametes that can be produced from this is big A, big B, big A, little b, big B, or little a, little b. Okay, so in this case, order is more important. So in this case, 4 gametes can result from this particular cross. Okay, gene combination. So it could be big A, big B, big A, little b, big B, or little a, little b. Okay. Now this one's the same thing. This is what I call foiling. So do you remember back when you're taking algebra, when you simulate meiosis, you're basically what they call foiling. Okay. And if you guys remember what that is, it's first, outer, inner, last. Okay. And so when you're doing this, you basically, and you don't have to draw it out like this. I'm just showing you what's happening on the chromosomal level. So this can pair with this can pair with this can pair with this, and this can pair with this. So you can have the following allele types. Okay. Okay, so this parent, let's say that this is the female. This parent can create these eggs, right? And this parent can create this sperm, okay? So these are its gametes. These are its egg and sperm, okay? Okay, so the next thing you want to do, so we did one. And then I will, as we go through this, I'll also talk about some of the nuances of these things. We'll do a different cross. We'll do a couple of them. So we simulated meiosis. The next is you want to set up the cross. So what you're going to do is you're going to draw a giant, you're going to draw a giant table. And so what you want to do is you want to identify the unique allele or unique gametes that result from this. Okay, so we have big A, big B, big A, little b, little a, big B, and little a, little b. Now these are all different, so there are 4 unique gametes that can be produced from this particular cross. And this one here is also 4, okay? And so what you're going to do now is you're going to make a giant Punnett square that's 4 by 4. So you're going to draw, and I'll bring this paper back. You're going to draw a giant Punnett square that's 4, 1, 2, 3, 4 by 4. 1, 2, 3, 4. Make sure it overlaps. Just when you're done, make sure it looks like a big tic-tac-toe table, okay? What you're going to do is, do you see this upper left one? You're going to cross that out because you're not going to use it. A lot of people use that spot, and you shouldn't, so that's why I crossed it out. Great, now my pen's underneath this thing. Okay. The next thing you're going to do is you're going to line up these 4 gametes on one side, and then these 4 gametes on the other side. Okay, so remember, the egg goes on the left, sperm goes on top, and at the end of the day, I really don't care. So just whatever. Okay, so we have big A, big B. We have big A, little b. We have little a, big B. And then we have little a, little b. And then you're going to do the same thing on this side. The next thing you're going to do is you're going, okay, so I talked about earlier that order is more important than dominance, the dominance. When you bring them back together, order and dominance comes back into play. So recall here, order was more important. So we put that little a, and then we have that big B. Do you see that? This is because the order in this case is more important than dominance and recessiveness. But since you're bringing these back together due to fertilization, now order and dominance is important. So you're going to do the A's first. So big A, big B, big B, big A, big B, little b, big A, little a, big B, big B, big A, little a, big B, little b. Do you see how I'm doing top and bottom? Now in your text and everything else that you see, they're going to be side by side. I like doing it top and bottom because it's easier to look at the phenotype. Okay, so this is just my own kind of preference. So go ahead. Okay, big A, little b, big A, little a, big B, big B. Big A, big B, little b. Okay, so there's your cross. Okay, I might have done some wrong. I have quite a few distractions in my household right now. So I apologize if it's not perfect. I have not had coffee either yet. Okay, so what we're going to do now is we're going to analyze the data. So here we go. We set up the cross. Ooh, and we also completed the cross. So we get to cross 2 off our list. And then finally, let's analyze our cross. I'm never going to say, hey, give me the genotypic ratio, because that's just mean. I'm not a jerk. So, or maybe you think I'm a jerk. I don't know. Whatever. That's your deal. So the next thing you're going to do is you're going to analyze the phenotypes. So what we have 4 different phenotypes that can result from this. We have 2 the parental type, or we have 1 parental type, and then we have 3 recombinants. Recall that what recombinants means is that they look different from the parent. Okay, so what are the different phenotypes that we can have from this? We can have, let's see, we can have, let's see, yellow, round. We can have green, round. We can have yellow, wrinkled, and then we can have green, wrinkled. And so sometimes what I do is just to make things simpler, I just write what the genotypes would be in that particular case. For something to be yellow round, these are dominant, right? So anything that has a big A and a big B, and then I like to put a little dash here, that just means that it could be anything. This is going to be yellow round. Green is a recessive trait. So anything that's going to be little a, and then round is dominant, big B, whatever, is going to be green round. Yellow is a dominant trait. So anything with a big A, whatever, and then little b is going to be yellow wrinkled. And then the only condition in which is going to be green and wrinkled is going to be little a, little b, little b. Okay. All right, so let's go and analyze the data. Let's do yellow highlighter. So anything that is yellow and round will color in with this yellow highlighter, okay? Now, does this have a big A and a big B? Yep, this does. Oh, look at that. That does too. Whoa, magical. This does too. This does too. This is amazing. Oh, look at that. That does too. Oh, boy. Oh, look, this one does, and this one does. Okay, so anything with this particular phenotype, how many are there? Let's count together. there's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's going to be 9 of these. Okay, so there's going to be 9 of the parental types. Now let's go through, and with the green highlighter, we're going to, oh, wow, they all look the same. Okay, with the green highlighter, we'll highlight all the green round individuals. Okay, so anything with a little a, big B. So here's one, little a. This one, and also this one. So there's going to be, how many of those? 3. And then let's see, I'm gonna pull some more pens out. I have like 10,000, but none of them are unique. Ooh, orange. So yellow wrinkled, we'll make orange. Okay, and anything with a big A and 2 little B's is gonna be yellow wrinkled. So there's gonna be 3 of those. And then lastly, we will circle in pink, I suppose, anything green and wrinkled, and there's only 1 of those. Okay, and so there is 1 green and wrinkled. So the phenotypic ratio is going to be 9 to 3 to 3 to 1. Okay, now what did this tell us? This basically told Mendel that 2 different characters are going to independently assort from each other, which then gave us the concept of independent assortment, which is one of the major points of meiosis. Okay, and again, these are not linked genes; these are unlinked. Mendel was lucky; all 7 characters that he looked at with P's, they happen to be on different chromosomes, and that there's only 2 allele types, and there are multiple alleles, as I talked about in class. And so he did get lucky, but I'm glad he got lucky, because if they threw in things like sex-linked or linked, then he wouldn't have come up with these concepts of independent assortment. Okay, I'm going to post another video. I need to resolve some things in the household. I will post some more videos about dihybrid crosses momentarily. Thank you.